So I'm going to click run simulation in our system,
Yeah.
and we're actually going to see a simulation kick off with 1,000 AI agents running a marathon through Las Vegas in real time. Um,
Actually, a
I think it's
thousand AI agent. Wow.
that's right, 1,000 individual sessions that are all communicating together with a simulator and a planner. So what we're looking at here is a front end that is communicating with a message passing gateway. We're going to dive into the architecture in a little bit. And I'll just follow the leader here just for fun. Each of these little dots is a runner agent session, and we're constantly checking on them with regard to their hydration levels and their velocity. And they're making their own independent decisions about whether or not they're drinking at water stations. We just passed one. We just passed another one. And that can change their energy. We're following the leader. That's the best runner, but we can also follow others that might be walking or jogging the race. And we can see, they have different paces.
So actually, every dot is represent. It's like simulating a real marathon runner, and they're gonna have different speed, and some of them have different hydration level, or they might hit the wall.
That's right.
And they might change their speed. So it's the actual real life simulation for trying to simulate the marathon.
Yeah, that is the idea. Exactly. And, it's a simplified version of what a real large scale event might be like, but it's a really good way to understand how to incorporate, multi-agent systems into realistic large scale projects.
That is so cool. I really want to learn how those dots, represent connecting to the actual session, and how do you, run them together so smoothly, so fast. And how do you actually simulate different session to map into the actual different type of runner, and how do you design this whole route? Yeah, this is very cool. Wow, can't wait to dive in.
We will definitely do that.
Yeah, I'm Annie. Welcome back to the channel. I was joined by Casey West, who is a brain, the builder for the whole system. Hi, Casey. Want to give a quick introduction of yourself?
Yeah, hi, I'm Casey West. I'm a developer advocate, just like Annie at Google Cloud. And I led the development of this agentic system, which we demonstrated at Google Cloud Next for the Developer Keynote.
All right, Casey, why don't you walk us through the architecture? I'm really curious to know how this whole cool demo is built. Actually, no,
Yeah,
not demo, cool production system is built.
Yeah, I would call it a reference architecture. It's somewhere between a demo and full production. I'm really looking forward to your community writing better code.
Yeah. Oh, by the way, this is all open source. So if you're interested, if you want to play around on your local machine, or you want to try it out, you want to learn architecture, you can always check out the source code on the screen. Let's go.
Yeah.
Casey, can we deep dive in this architecture?
Yeah. So before we get into any code, I want to ground us in the shape of this thing, because this is a somewhat large scale system. So we call it race condition. So race condition is based on 4 layers. There's an Angular front end, a Go gateway, a network of Python-based ADK agents, and the infrastructure that those agents live on. So, our first question that I think we need to answer is, why is this a polyglot stack? Why do we have a stack comprised of so many different types of frameworks and languages? And really, it's just because we wanted the best tool for the job. So Go is what we use for a high concurrency traffic cop. It can handle, as many WebSockets as we need, and thousands of messages being passed over those connections without breaking a sweat. And Python is where all the AI lives. So that gives us the access to our entire ecosystem of LLM tools using ADK. And, ADK in Python is a really mature and rich framework. And this separation is why the system feels as snappy as it does. So even with 1,000 agents that are all thinking at once, we still have, the speed and efficiency of the system. So for developers, it means that we can isolate our agent logic in clean Python modules, while the Go layer can handle all the heavy lifting of real-time communication. Does that make sense?
Yeah, so it sounds to me that maybe it's a good summary can be, we have 4 layers. We have front-end layer, which have those cool simulation. We have a gateway layer to handle the communication from the front end to the back end, so that we can have 1,000 simultaneous session together because it's more resilient. And then we have a backend layer with ADK Python to handle all the agentic system logic with ADK. And then we have an infrastructure layer with like Redis or PubSub so that we handle the whole communication protocol and handle the whole, as an infra to handle the whole communication system pattern, stuff like that, right?
That's right. That's right. Well, this open source repo has a lot of documentation we've tried to include to help people navigate, but one of them is a system architecture. And this mermaid diagram is where we can start to explain the project. And I know there's a lot here, but let me break it down a little bit. I would consider this to be the one source of truth for the repo about how everything fits together. We can see that the things in blue all live in the browser. So, the user starts by interacting with the simulation UI. We've got some admin dashboards, some other things we'll see later. And then green is what's written in Go. And these Go services are like the backend for front-end systems. If you're not familiar with that pattern, it's where we have a small backend layer running, say, in Cloud Run that the front end can communicate with, and it'll proxy messages back to other parts of the architecture. Orange is all Python. We can see that down here. These are all of our agents. We have a planner agent. We have different types. We'll talk about that soon too. Simulators, runners, which we discussed in our intro. And then we have purple, which is the infrastructure layers. So, the gateway, which is the central layer where everything communicates back and forth, talks to the agents, and it can talk to the agents using two different types of transport. So we can have HTTP-based orchestration, but we can also have PubSub-based or event-based orchestration. So we'll dive into how that works as well. Right here, we've got, two dispatch modes. So the runner agents are the ones that are going to be the highest scale. That's where we might have 1,000 sessions running all at the same time.
I'm so curious about two different modes. Like you talk about subscriber mode and, just normal callable mode with HTTP call. Maybe you can explain more about that?
Yeah, that's right. So we have these two dispatch modes. Internally, they're called subscriber and callable. So subscriber would be this Redis or PubSub mode. And subscriber agents will hold a long-lived Redis subscription. Every tick or every time we sample data when we're running the simulation, the simulator will publish a message on Redis that will go to all of the agents simultaneously, and they'll all wake up and respond. And that allows us to interact with these ADK agents with no HTTP latency, and those interactions can happen in sub-millisecond times.
Wow.
And we only need that for the runners, and that was an optimization that was really important.
Yeah.
But for all of the other agents, the planner agents, simulator agents, and their variants, they are what we call callable. And they just sit there, on agent at runtime in Gemini Enterprise Agent Platform, waiting for an HTTP request. And we only need to do that occasionally compared to the runners. So we can just interact with them using standard A2A HTTP protocol. So A2A being agent to agent protocol. So they just do their work and go back to sleep, and they can scale down to 0 just like they normally do.
I see. So it's like a simulator agent send broadcast a message, say, oh, tick 1, tick 2, and all the runner saw the message at the same time. So they're gonna update the distance, update the location on the map. So is that how it works? So they can see things on Redis,
That's exactly right. And this allows us, to not pay for a bunch of idle CPU for the thinker agents like the planners and simulators, but for the doers, which are sort of the hot path where we have a lot of simultaneous sessions happening, we had to have this efficiency. So this is a really interesting technique that can be reapplied into a lot of other environments. And I think we'll dig into it a little bit later, but each of the runner agents extends the A2A protocol by defining in their agent card, which is another A2A concept, what type of callable methodology they use. So, or which type of dispatch they use.
Yeah. So I'm curious, before you build the system, do you already design what is the callable, what is the subscriber, so that you can start to configure here, or you gradually figure it out?
That's a really good question. So I gradually figured it out. So I started by trying to do the normal sort of common scenario, which is that we would just do A2A based agents that only speak over HTTP, because that's how A2A is designed by default. And of course, my goal is to try and use the tools, the frameworks, the standards, the protocols as they are designed. Thankfully, the people who designed A2A also built in a mechanism for extensibility of the protocol. Because what I found out is that there are a number of reasons why this doesn't work when you want to send 1,000 messages to 1,000 different agent sessions at the exact same time, and you want to collect responses from those agents as fast as possible. In our case, we need those responses within approximately 10 seconds. And that might seem like a lot, but it turns out once you optimize your agents and your communication pathways, really the network becomes the bottleneck. And we're going to talk about bottlenecks a little bit later.
Sure.
But basically, I determined that for a couple of different reasons, which I don't want to give away just yet, the runner agents over HTTP would not scale up to meet that need efficiently. And we would have a huge amount of network overhead with HTTP that was unnecessary if we used Google Cloud's memory store service, which is managed Redis. And managed Redis has a pub sub built within itself that can handle, I think it can handle approximately 100,000 concurrent messages incoming per or simultaneously, just with a single node. So even on a small instance, it can handle way more than what I needed. So that was the right choice for sure.
Wow, thanks for sharing your thought process. So essentially you start with all HTTP-based A2A call, and then you realize that it's not suited for the system need, because we want 1,000 simultaneous session handled at the same time, and we want to making sure it's a good user experience. Basically, it has the speed is good, the performance is good. So then we iterate to this dispatch, to this subscriber mode, and with Redis to handle the memory situation.
That's definitely right. Yeah, exactly. So I want to follow or continue a little bit. So if we get into the gateway, which, as I mentioned, is like the high bandwidth message passing layer. The gateway sits between all of the front ends and all of the agents, and all of the messages that go through the gateway. And the gateway is what will read the dispatch mode and try and figure out what to do with it. So in this case, this is just some code that tries to understand capabilities defined in the agent card. So we'll get to agent cards in just a second. In fact, I think I can show you one now. Why not?
Yeah, agent card basically is like an agent identity, similar to our, LinkedIn profile, our name card. Agent also has its card, so that other agent understand what it does, what is the capability, and how to communicate with it, what are URLs, stuff like that. And Casey is going to show us what is the identity of this agent.
Yeah, so in this case, this is an agent that is running locally. It's on port 9105 in this case on localhost. And this is the planner agent. So how do I know that? So let's see here. The name is right here in this JSON payload. This is the agent card itself. It's the planner agent. You can see that within an agent card, you can define its description. So this is an expert analyst for marathon route and event planning. It has skills. So in this case, one of its skills is that it can create a detailed simulation plan, right? That's what it's supposed to be for. Here are some examples, that sort of thing. So these are all of the skills of the agent. But the thing that I think is really fun is that you can define capabilities and you can have extensions. So I defined an extension using A2A. This is all part of the standard protocol. that was the callable methodology. So how do you interact with this agent, essentially? So if you read the agent card and you can understand this, then you can see N26 being for Google Cloud Next 2026, N26 for short. Dispatch, this one is callable. So this is the dispatch method, right?
Yeah.
Is callable. And then if we showed the runner, which let me figure out which port that runs on. Just a minute.
So we can also change this dispatch to subscriber if you want to change.
Yeah, so let me go to port 108, not 9108, and you can see that this is the runner agent, right? And it's a subscriber. So this is the way that the gateway service, it reads this and figures out what method to use. So if I go back to sharing the code and we look at our catalog, you can see that we're reading the extensions. We're looking for, subscriber, or we're looking for the dispatch method, and then we'll figure out what it is, or we'll default to subscriber because it's the most efficient version. So subscriber is the lowest overhead, so we'll default there. So that's how this code works.
So now I have a much better understanding of the overall, what are the components, what are the layer, and how they communicate, how we define the dispatch mode. But the next big question is why we want to use this agent to plan the marathon.
Yeah, I mean, honestly, you could write this whole thing as a procedural simulator. You could loop through the runners, call a function for each tick in the simulation. You could write telemetry to a log and you'd be done. But the reason that we reached for ADK was everything around the LLM call. We needed lifecycle management around the LLM. And we also needed sessions to live across requests. We needed callbacks so that we could intercept or interpret model calls and tool calls. And we also wanted things like A2A. So, agents could discover one another without being hard coded into each other's configurations. And we also wanted telemetry and, a dashboard that we could subscribe to. If we built all of that up from scratch, with deterministic code only, it would get really cumbersome. But ADK gives us all of that for free, and it gives us the LLM interaction. So I think that's a big reason why we do that.
I see. So it's not only relying on, just simply using AI, it's also relying on the benefit of using ADK agent, because we can take advantage of the life cycle it naturally have, because we can intercept a different part of the life cycle and how we have the communication protocol with agent, and we have telemetry, tool calling and stuff like that. So we can leverage the whole nature of the agent system. So that's a major reason we want to use agent system, even though we have some deterministic logic here. Is that
yeah. ADK gives us all of that out of the box. So, for all of you as a developer, it means that you can focus 100% of your time on intelligence and, the prompts you need to write rather than the plumbing of distributed systems. So that really helped us get a lot of this built out in weeks rather than months.
Cool. I have another reason why I should build this ADK now. Why do you explain more about the ADK agent so that we understanding better about what is ADK agent, why use ADK agent, what are the benefits we have? And
yeah, let's look at an ADK agent right now. So in the code right now, we have the ADK agent for the planner. So this is really it here. You can see that we have an LLM agent in the planner agent.py, and the name is planner. And we have a model here that is wrapped in what we call a resilient model. So this is a little side note, a little tip, but
it's more resilient.
ADK. What's that?
It's more resilient.
It is, yeah. So ADK by default, when it tries to call a model, if that model call fails for some reason, maybe you hit a quota limit or there was a network outage or just like a little intermittent failure, it will just fail. But ADK is built on top of Google's Gen AI client libraries, which are the unified client libraries for accessing Gemini models and other models through Vertex AI across the board. So it's a really robust client library for all Gen AI interactions with Google Cloud. And that client library has a lot of capabilities for doing things like automated retries with jitter and backoff. So all of the resilient defensive programming capabilities that we're used to in large scale distributed systems, that's been baked into that lower level client library.
I see.
And you can define a custom model object that basically turns on all those capabilities and then pass that to ADK. So ADK can get those features too.
I see. Is that like auto retry? For example,
Yeah.
if I have some 429 quota exceed error, or I have a different error with, for example, image generation that's specific. There's some filter and you need to regenerate. So basically it's handle the redo automatically. Is that a good understanding of resilience?
That's exactly right. It will retry. I designed it specifically to manage the 429s when that would happen from time to time. But then in addition to just retrying, it will also do exponential backoff. And what the other best practice in distributed systems design like this is to do a little bit of jitter. So you just make a small variation in the backoff and the amount of time it takes between retries. So it's not just so consistent. You don't want to retry immediately 5 times in a row. And you do want to back off a little bit and give the network time to catch up or to recover or to heal. So all of that is built into this concept of a resilient model.
Wow.
If I scroll up here,
yeah, while you're looking for it, I just want to say, no wonder the demo is so smooth, so reliable, even though it's built with AI. It's like, cool. Now I know one trick.
Yeah, so I probably should be a little bit better at code search in my IDE, but nevertheless, this is in the code base. So if anybody wants to take this and use it in their own code, they can. But we have under agents utils retry.py, there's a resilient model method here. So you give it a model name, and you can also give it some retry configuration and maybe where your model is located, that sort of thing. And it will return this global Gemini object with the model, the retry options that have been configured, and there are default retry options as well.
Oh my God. This is so helpful. It helps the pain point I'm using model for now. This is
for sure.
I'm gonna do after the session. I will like use this code for my existing agent.
Mm-hmm.
And also
that's great. Yeah. So
hair color.
The hair color change it helps all development go better, obviously. But in our default retry options here, you can see, just like you were describing, we have the maximum number of attempts, the initial delay, the maximum delay, the jitter, and the exponential backoff base. The other thing to know about this is you saw the global Gemini object. So global Gemini. The reason that this exists is because GCP, Google Cloud, typically only makes available preview models that are not GA yet in the global region and not in specific regions. And ADK, at least at the time of this writing and this recording, doesn't have an easy way to bypass that, especially on agent runtime, or what used to be called agent engine. So in Agent Engine, we didn't have an easy way to specify that we wanted a preview model like Gemini 3.1 Pro Preview or Gemini 3 Flash Preview. So you can actually get around that by providing a custom model to ADK. And so that code is in here as well in a global Gemini.py that you can also find in the utils. So this will make it really easy for you to target a preview model, something that's, our latest, our greatest models, and do that on agent runtime. If you were doing it locally, you wouldn't have this problem, but you do have this challenge in agent runtime right now. So this is a way to fix that everywhere.
Wow. Yeah, I did have this pain point as well. I'm using some latest preview model from like a Flash model and video Nano Blender Pro and a live model. They're all preview in the global location. Yeah, this is so helpful. Oh my gosh.
Yeah, but this is the whole agent. This is an LLM agent. We give it a name, a model, a description. We give it static instructions. So static instructions or regular instructions or both. This is an ADK feature. Static instructions are they'll never have variables that might be replaced by session state. So they're more likely to be cached using server-side caching with Gemini, which will make your agents more efficient. They'll make them faster, and they'll also make them cheaper because you can have session-based context caching. So I use static instructions here, and then I have what do we call it? Yeah, a prompt builder that can build a prompt based on some basic criteria. And because this is our basic planner agent, it's sort of the first version of a starter agent. It doesn't take any parameters. It just builds the default profile or the default instruction.
I'm curious, the static instruction, is this automatic inject to the context window? Is that right?
Yeah. So the way that ADK constructs a session history in order to send a prompt to Gemini is that it starts with your static instructions if you have any. And what you want to put in static instructions are essentially any instructions that would be the same across multiple invocations of the agent session or across the board. So that can be the bulk of your prompt many times for many use cases. And that session caching really comes into play on like the third, fourth, fifth turn that you have when you're interacting with an agent session, because the static content was most likely to get cached by ADK. And then you can just reference that ADK and Gemini for server-side context caching. And then you can reference that cache. And the ADK framework has all of the plumbing and stuff built in to already do this for you. And then the next thing that it sends is your regular instructions, if you have any. And those instructions can include variables that can be replaced by session state variables. So if your session has accumulated state variables, they can actually be interpolated and that'll be sent.
I see.
So those might change on every turn, right? Those instructions might change. So those will be sent. And then, of course, the series of events. So the user message comes next. And then if you have a long running session, you might have additional messages that get sent based on, the agent response and the user response back and forth.
Gotcha. So static prompt is more, it just loaded there for more efficient use because we have loading more prompt with like prompt with variable injection or like a session state. That's something that's dynamic. So we want to load the static to improve the performance.
That's right. And since we're on prompts, we might as well dive into that too, right? So I actually have that file here. So this is the prompt system for, actually we can start right up here. So this is the planner prompt. And this text here is markdown based, and it's the instructions that instruct the planner to do things like load skills on demand. And the critical concept here is context window management. So when we tell the agent to only run load skills, like right here at line 54, we've got this skills section. We say only load skills on demand. So this allows us to isolate the capabilities of the planner agent into a series of skills. And those skills, which we can also dive into, is instructions and maybe also tools that get bundled with those instructions. And we only want to load them into context when we need them. So in this case, during planning, we only want to load these skills. But if our planner agent is asked about financial information, then we should also load skills based on that. So
it's like
that's how we do it here.
It's dynamic loading so that it's not consuming the context window and only use the skill when need. So I'm curious, the skills part, is that how we're going to dynamic loading the skill? Is that right? Is that what it is?
Yeah. So ADK has these load skill tools and a whole series of tools around loading skills. So all we have to do here is instruct our agent. We can say load skills on demand using the load skill tool before calling their tools. So in this case, then we explain, here are the planning skills. We have a GIS spatial engineering skill and a report marathon that has these tools, plan marathon route, report marathon route, that sort of thing. So the idea here really is, and if we looked at the life cycle of the planner agent, when we ask it to plan a marathon route, we would see it do exactly this. We would see that it would call the load skill tool, and that would load the skill. It would get the skill back. It would understand. It would add to its context what tools are available and what instructions it has now, additional instructions, and then it would call the plan marathon route. It would call report marathon, and then this one is interesting. So we also get.
Hi, sorry. Okay, please continue.
That's cute. Yeah, so we also have the ability to get some information from Google Maps MCP server, but only if it's available. So Google Maps MCP server requires you to create an API key for it manually, and there is no automated way to do that. So in order to make this easy for developers who want to explore this code base with open source, I also made it optional. So if we don't have an API key for Google Maps MCP server, then we just won't access or use the Google Maps tooling. And that works with and without. So that you can also see here in step 5, if mapping tools are available, then we can go and look up things like weather data to try and find a suitable time to start our route, that sort of thing.
Yeah, for those of you who don't know
So
what is Google Maps MCP server, basically Google has a managed MCP server that help like you easily connect and use Google Cloud Service. And here it's a Google Map MCP server is help you to easily using Google Map.
So you mentioned how do we get the skills? So skills are, and maybe this is a good opportunity to actually share in the code browser here under agents and planner, we have skills. Then we have GIS spatial engineering. And so under the skills directory, and by the way, so ADK sets out a directory structure. You can find it in ADK's documentation at adk.dev is the new URL for ADK documentation. But you can find it there as well. And you can see that for GIS spatial engineering, we've got the skill.markdown file. So if we look at that, we can see, let's kill that. So for the skill.markdown file, we can see that its name is GIS Spatial Engineering. And in the description, we say, use this when the marathon needs to plan, a specific route. So it tells your agent, this is context that gets loaded into your ADK agent when you load this skill that explains how to use or when to use this skill. And also there's metadata that explains what additional tools will you be loading into this agent now that you've loaded this skill. So this lazy loads tools as well as context. And I think that that's a really important feature. I know skills are kind of all the rage now. Everybody wants to build skills for everything, but this is how you can build skills for, agents that you'd be running in production environments.
So with this, we can load lazy loading the skill visa. ADK know how to when to load the skill and how to load the skill.
That's right. And of course, in our prompt, we explained on step 2 for the planner, we said load the GIS skill, and we gave it an example of how to do that. There's also some code in, loading ADK tools where we can go and find our skills and just make sure that we understand what our skills are. I mentioned ADK has these features built in. So ADK has the skill toolset capability. So we can read the metadata about those additional tools and also load those in a lazy way here. So there's a little bit of code in here to check that you can check out for how to do that as well.
Cool. Also, another thing I'm very, very excited to try right after the session. Keep adding to my to-do list.
I know there's so many things to talk about here. Let's see. There's also, how do the agents communicate over the gateway to the front ends? I think that's maybe another important piece. This is a large file. It's probably too big. So again, I'll be looking for PRs if people want to help me refactor my code base. That would be amazing for me.
Please, everyone who, if you're watching till now, please help
Yeah.
Casey, help us improve.
Yeah, exactly. Yeah, so this is under agent utils and it's called communication.py. So this is loaded into every agent, but this is really the last code stop for this section, I think. When the planner needs to call the simulator, for example, these are two different agents. And I chose to use this call agent tool that I loaded everywhere as a wrapper around A2A based interactions. So this abstracts away the networking because what we're actually doing is sending messages to the gateway service that we talked about before. And the gateway service is routing those messages and sending them to the correct agents. And as you get a larger scale system, one of the things I wanted to be true about this multi-agent system is that if they needed to or wanted to, any agent could communicate with any other agent in the system. So you can think about it like a mesh network for agents, as opposed to like a directed graph where only an agent only talks to another agent based on a predefined workflow. I wanted to have the option for all agents to communicate with one another. So the planner doesn't know where the simulator is running at all, right? It just says, using this call agent method, it just says call the simulator, right? And then ADK through this communication layer handles the discovery. It'll retry if it needs to, if the agent didn't respond right away. And maybe one big reason for that might be a cold start. If you are scaling these agents to 0 and they haven't been sent a message for a while, they might time out on a cold start. So you might want to try again. And then, so it'll send the message, it'll retry, it'll emit the pulses or the messages to the gateway for telemetry as well. So we'll see that in dashboards. And this is like the single entry point for all agent to agent chatter. And it just wraps A2A in this really reliable function call or tool call.
That's pretty cool. So only callable agent will have cold start, right? For the subscriber, they're always subscribing, so they don't have cold start.
Typically, that's certainly how I did it. So I decided that because the runner agents needed to respond instantly to any messages, I had at least one hot instance always running. And the runner agents actually were deployed to Cloud Run instead of agent runtime because I had more control over the scalability characteristics of services running in Cloud Run than we currently do with agent runtime. So Cloud Run has just more tweaks and knobs to dial when it comes to the way we deploy them. We can configure specific concurrency configurations and hot and cold instances up to as many as we want almost. I mean, there are real limits, but we weren't close to those limits because Google Cloud can handle a lot.
Yeah, when you say you want to have the meta network so that every agent can call, like potentially connect to another agent, that's why we want to wrap a call agent with A2A protocol. So how does is that why, first of all, you haven't defined a workflow agent, you define a workflow prompt? And secondly, who decide which agents interact with another agent?
Yeah, so the workflow prompts were because LLM-based agents needed to make decisions about how to execute the workflows. A big reason for that is because we were building a multi-agent system using Gemini as a core tool to demonstrate these capabilities.
Okay.
I mentioned before that like we could have done this fully deterministic, but then we would have had a lot more work on our hands. But in the end, even though every agent could talk to every other agent if they wanted to, what ended up happening, of course, and this is, I think, true of most real systems, is that we had some predefined or some clearly defined workflows that existed that kind of made the communication structures more visible. So, and more deterministic, I suppose, is maybe a way to say it. So we always knew that the planner agent would need to do evaluation and talk to the simulator agent when it's planning a marathon. And then when we want to run the simulation, the planner agent will ask the simulator agent to run it, and the simulator agent will communicate with the runner agents. So we kind of establish that early on, but if we had more time, a larger vision of this thing, which actually is in the README of the project as well, for ideas to expand it. So again, I'm looking for, pull requests and contributions from the community would be awesome. But a larger vision of this is that we had even more agents in the mix that might be able to interact with one another. So a good example would be if we had a public service or a public safety agent that was maybe trying to make sure the runners were safe from traffic and that the cars were not going to cross the marathon route when they were trying to drive across the city. Or if we had businesses represented as agents that might be impacted by the marathon. So if you had a drive-through food service business and the marathon closed your street, that would be bad for your business maybe. But if you had like a walk-in coffee shop, that would probably be very good for your business. And it would be interesting to model that as well. We never got that far because we had a limited amount of time and a limited amount of scope. But in those cases, we could have agents interacting with one another directly. Maybe a runner jumps off the route and goes and gets a coffee, or maybe a runner tries to cheat and cut across a street and try and win that way. Like, it would be interesting to try and catch them and see what happens in those scenarios. So
yeah, it's like a movie or a game. Yeah. That's so fun. Yeah. So
well, what's cool about having an LLM in the mix is you can get chaotic and unexpected behaviors. You still have to sort of prompt the possibility of that. Mm-hmm. But I think it'd be really interesting to expand the runners with a sense of identity where maybe a runner like follows the rules and has been training really hard, and maybe another runner wants to cheat, and we could, write that into a prompt and see if they could get away with it. And then we might have to have like other agents that are looking out for cheaters and seeing if they can find them.
Yeah.
So that's the architecture for this episode, but we skipped the most interesting decision of all. When does the system actually use AI, and when does it skip LLM entirely? So in the next episode, we will see how does it scale to 1,000 agents all at once. Alright, I will see you in the next episode. Bye!